start with showing like it's not the myosin, it's a side package. So this is shiny myosin shiny. So you can like it uses myosin, but with in a shiny app, it's not as efficient and you don't have as much control, but it should be the first place so you can understand the models and kind of see what they do, what the parameters are. You can install it with, so you can install it from GitHub. So it's explained in the page, and then you can just run it locally like this. And then once you have it, you can choose the model. So here we have the, for instance, a Hubble model, the logistic model, the generalized lot-level data, and the consumer resource model. You have the parameters that you can define here. There's some implemented examples. Just close this up. So if you click on them, so they're described here. So this description, I'm going to go through this later, just but they're described here, and then you have the examples saying what they are. And then in the model, you can click and it will generate this example for you. And then you have a set of parameters that you can manipulate here. You can change the number of species. You can define your own initial composition, and this updates in real time. You can, there's some perturbations. It might not make a lot of sense in the Hubble model, but it's just a general interface. You can try to add growth rates because it's implemented with a Gillespie algorithm that I said, so you can plug in growth rates and then it's not neutral anymore. But you can do that. And yeah, that's, so all the, as I said, you can go through these models. And then I'll just show the, so if you install the package itself in R, so I'm going to show through this this notebook. This notebook is also there in the Shiny app, so you can read all the descriptions of the models, and you can see the examples. So I'll start with the Hubble model. So this would be like a simulation of the Hubble model with some default parameters. Of course, if you would go here in R, you would see all the parameters that you can specify, the full list of parameters. And then you can plot this. So this is updated to MyAviz. I think Leo will talk about it. So this is, apologize, this is a previous version. So I made like a plotting function to plot the results, but now it's integrated into MyAviz. That's like a package to visualize the myosin environment data. And then you would just do something like this. So simulate Hubble rates, that's the name of the model, just by defining the number of species. And then you get back an object that you can get all the results from the simulation. So for instance, you have a simulation. If I set the migration parameter to 0, then what you would expect is that one species will dominate, and this is what happens. You can change the time, so you have the control of the time. Like here, this is an example where you have, so you can say, when do you want to end your simulation, how many time points you want to store, so how many intervals of the simulation you want to store. You can also start from a different time point. And this is an example where we have everything from the migration probability is 1, so the distribution in the end is only what you give as the meta community probability. Let's see if there's anything else. So this would be the Hubble model. It's not maybe the most interesting one. Then the logistic model. So the model without interactions, the same thing. So you have a description of the model. You would do it like this. So simulate stochastic logistic. You just define the number of species, and then it's going to fill everything else with default parameters. If you, just want to see immediately how a simulation would look like. But then, of course, you have control over all the parameters that you can change. For example, you can give death rates or not have death rates. If you don't have death rates, then you would have a simulation that goes like this, so the species never die in time. If you put death rates, they die. So here it's an example giving death rates, so the species, they go down over time. You can define the carrying capacities, and you can define growth rates. Of course, if you look at the help of the function, everything is very well explained. So all the parameters are very well explained, and you can already do a lot of different simulations. And then you can add errors and noise. So this is an example of a measurement error. So it's an error that's not correlated, and it's not does not integrate into the simulation. So it's added in the end of the simulation. So it's not it doesn't accumulate through the simulation. It's also, so this would be the logistic model. The generalized Lotka-Volterra model, you would have, it's also, I mean, the interface is all very similar, like that one. So you simulate the GLV. You say the number of species. So with this is already enough. So all you need to say is the number of species, then it's going to generate the random matrix and all the rest. But then you can, change your parameters. So one thing that you can do, so we have a function that's random A. So it's a function to generate the interaction matrix. And then you can define, of course, the number of species. You can define a specific value for the diagonal, or you can also give a list with a vector with values. So you have different values for the diagonal, if that's interesting. You can define the connectants. So this is going to define kind of the proportion of like 0 off-diagonal elements. You can say if you want to scale the off-diagonal elements proportional to the diagonal ones. You can say if it's symmetric or not. There's other options here. They're not here. For example, you can give the proportion of competition or the proportion of of commensalism, of all kinds of interactions that you want as an option. Then it generates the matrix like here. And then with this, you can plug into the previous functions that was to simulate a GLV. You can also have stochasticity implemented. I think, as I explained in the talk, so there's several parameters that you can add for stochasticity. You can also define a migration probability and a kind of a meta-community probability that's going to then add migration to the model. And this example, maybe not. See if there's anything. Yeah, and also measurement error and noise, the things that you can add. So here I would just put an error variance. So this, if you look through the help of the function, it explains all the error terms. So the error variance would be a measurement error. Yeah, this was just a replication of these results. So we tried to replicate several results from literature. This is kind of not unfinished because there's a rounding here that we don't see, and also it's not the same when you use R as a solver. It's not as stable when you use MATLAB or anyways. But we more or less can reconstruct the same pattern. So you see when you increase the amount of interactions, the strength of interactions, or the amount of species, then you start getting these funky oscillations in the right. And then I will show real quickly the consumer resource model. So again, a description of the model. I'll go a little bit slower on this one because this is the most complete, maybe one that we have documented. So you could, like, first the very default one. So you have a number of species, the number of resources, and then you use the same kind of thing, simulate consumer resource, define the number of species, the number of resources, and then you can make a plot. So all the other parameters they're going to be, they're going to be set for you with some random distributions according to the parameter. It's all documented. And then you get the simulation of species over time and also of the compounds over time. Then there's some additional parameters. So here you also have this resource matrix that we're calling key. So you can generate a random resource matrix, and then again you have several control parameters over it. You can, like I said, the amount of time. So you want to run the simulation until when, how many data points you'd like to store, the migration probability, if you want to use the stochastic behavior or not, then the amount of resources. And then in this matrix, the positive entries, they're consumed, and the negative entries, they're produced by the species. You have, you can add some operation modes. So there's no death rate in this model. So if you use like a batch mode, there's no death. So then it would look like a chemostat, but if you set the inflow rate and outflow rate to 0, since there's no death, then the species just go to a stable value like this. But you could also, so you see the volume doesn't change over time. You can do some fed batch. So you can say, what if I just add in volume, like add in media, and then the volume would increase over time. Basically, you could try to do a chemostat, so that would be, remove and add at the same amount of value continuously over time, like this, and the volume doesn't change. You can also simulate serial passages. So this is like common, people do this in experiments. So you would have to control like the time when you do the passage. So at each interval of time, you pass a certain amount of volume to a fresh new community and simulate again. So you would have this. So the resource matrix, there's this maintenance. So if you like define a proportion by which, so threshold by which resources that are consumed they can give as output in resource produced. So there's like an energy budget, and you can define that with this parameter, this maintenance parameter. This is an example of a food web, so an anaerobic food web. So here we have a bacteria that feeds on sugars. That's a homofermented. You have a bacteria that's an acetogen and a butyrate producer, and they cross-feed. So basically, they all feed on glucose. So you see glucose is depleted very quickly. So all of this you can put in like when you call the function, you can add the names of the species like this, the names of the resources. And then you see glucose is consumed very quickly. They produce acetate, so the acetogen produces acetate. And then there's this lactate that first it's produced, and then it's consumed by the butyrate producer, and then the butyrate producer makes butyrate from lactate. So this is like an anaerobic food web that's, and you could talk about like preference for certain substrates. So you can give weights for substrates. So for instance, if you have resources that are not like equally liked by bacteria, like let's say bacteria prefer glucose and maybe lactose than ribose or sorbitol, then you can give weights to this that we're calling here trophic preferences. And then when you generate this matrix, it's going to be sort of weighted towards favoring the ones that have a higher score here. Like you can see here, there's like a bias towards glucose. You can also make this hierarchical. So like I said, like there's like this groups that prefers a certain substrate, and then a group that prefers a substrate that's secreted by this first group. And so it would be like the trophic level. So for instance, you have, so what's positive is being consumed and what's negative is being produced. So you have the first one, sorry, I don't know if I can interpret this very well, but just a second. Yeah, so you have two levels. So one level sort of prefers this substrate, and the other level prefers to consume this substrate. So it will be species here and the substrates. You can also do these like nested trophic levels. So if you have like a more complex structure, like this network here, and yeah, sorry, I'm rushing maybe a bit, but you would then let's see if there's something. Yeah, you would then define, the trophic preferences and get a matrix that goes according to that to this network here. And then you can simulate, and same. You would here let's see if there's any novelty here. So you would, yeah, I don't know, just give the names of species, the resources that you define, and the trick here, like how you control this dynamic is all in how you make this E matrix. So this is the E matrix. So you would make the E matrix according to that network and then simulate it. Let's see what else. Yeah, so the other thing that you could simulate is if there's, like instead of like sequential feeding. So first a species would feed on a resource, and then once it's depleted or it reaches a certain level, then it switches to another resource. Then you can do that by defining like a matrix of priorities, and then the species would go to its preferred substrate in order of its priority. And then you would get these kind of dioxic like behavior in the growth. Anything else? Yeah, so another advanced feature that you can do with the package is that you can try, so this is commented out because it takes a long time, so I can't show it now, but what you can do is you can like if you have a random model parameter or something like that, so you can generate kind of a batch of models, so you can simulate it multiple times. So there's this function here that's called yeah, now it's called generate simulations. When I wrote this, was called generate moments, where you define an instance of a model, like here, and you say how many like instances do you want to generate of this model. So for instance, 100, and then it's gonna, solve the model 100 times because there's some stochasticity. Things are going to be slightly different, and then you get a range of models, so you can summarize them by their average or something like that. And the idea here is that you could then plot the UMAP like with the communities and see if they cluster with certain model parameters or with certain variations. The last thing that I'm going to talk about is when you add noise and measurement errors. So I mentioned this in my talk. So you have this drift. So there's a general control that you say if it's stochastic or not, so you don't have to worry about all the specific things. And then you have all these different possibilities. So you have drift, you have some epochs, you have external factors, you have the duration times of external factors or the specific times when they affect the community, and also the measurement error. And then you can do, things like having a perturbation at a specific point that lasts a certain amount of time. And that's implemented in all the models. And the last thing that I said, but I did mention this, is that, the parameters, the output, the inputs, they're all consistent between the models. So then you can, compare them when it's possible to compare. I think Leo will talk more about this.